No, però prova dir-ho en directe al YouTube, si tenim més temps, ara perquè no la mano.
Però no hi problema.
Sí, però...
Com que tu ens diguis.
Vale. De moment avui així. Jo no em recordo. No, però prova dir-ho en directe al YouTube, si tenim més temps, ara perquè no la mano.
Però no hi problema.
Sí, però...
Com que tu ens diguis.
Vale. De moment avui així. Jo no em recordo. No, però prova dir-ho en directe al YouTube, si tenim més temps, ara perquè no la mano.
Però no hi problema.
Sí, però...
Com que tu ens diguis.
Vale. De moment avui així. Jo no em recordo. No, però prova dir-ho en directe al YouTube, si tenim més temps, ara perquè no la mano.
Però no hi problema.
Sí, però...
Com que tu ens diguis.
Vale. De moment avui així. Jo no em recordo. No, però prova dir-ho en directe al YouTube, si tenim més temps, ara perquè no la mano.
Però no hi problema.
Sí, però...
Com que tu ens diguis.
Vale. De moment avui així. Jo no em recordo. No, però prova dir-ho en directe al YouTube, si tenim més temps, ara perquè no la mano.
Però no hi problema.
Sí, però...
Com que tu ens diguis.
Vale. De moment avui així. Jo no em recordo. No, però prova dir-ho en directe al YouTube, si tenim més temps, ara perquè no la mano.
Però no hi problema.
Sí, però...
Com que tu ens diguis.
Vale. De moment avui així. Jo no em recordo. No, però prova dir-ho en directe al YouTube, si tenim més temps, ara perquè no la mano.
Però no hi problema.
Sí, però...
Com que tu ens diguis.
Vale. De moment avui així. Jo no em recordo. No, però prova dir-ho en directe al YouTube, si tenim més temps, ara perquè no la mano.
Però no hi problema.
Sí, però...
Com que tu ens diguis.
Vale. De moment avui així. Jo no em recordo. No, però prova dir-ho en directe al YouTube, si tenim més temps, ara perquè no la mano.
Però no hi problema. Però no hi problema. Però no hi problema.
If it's taking your microphone, maybe it's.
Yeah.
Let's try now. Is it good? Can you hear us? Yeah, there is some. Yeah, there is some.
That's funny. Has the sound disappeared again? No. Yeah, that's right.
Somebody else's voice.
Yeah, is it somebody joining the Zoom or something?
Let's try now. Is it good? Can you hear us?
Yeah,
There is some. Yeah, there is some.
that's funny. Has the sound disappeared again? No.
Perché tendríamos en bucle. Vale, ahora.
Tu puoi entuberar, no?
Pues sí, te toca la página, ¿no? A ver.
Vale.
Ok.
Ah, tenies els oberts. Potser sí, n'hi havia dos que feien bucles en el segon.
So sorry about that. Let's
Yeah.
hope we can stop listening to weird voices.
Yes, I'm very, very happy that everybody else heard the voices and they weren't just in my own head. Yeah. So the Kalevala says that the way the universe began was that there was a duck and it laid some eggs on the knee of the goddess Ilmatar, who happened to be floating around in this giant ocean. So one of the eggs broke. So this is in fact Ilmatar, and that's her knee, and there's the sotka, the duck, and the halves of the eggshell became heaven and earth. The white of the egg became the moon, and the yolk the sun. So that this is the way Kalevala begins, and here's the finish. Tuli sotka suora lintu. So Kalevala goes on with this rhythm for a long, long time. Da 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 da. And every line is repeated twice. So that's very poetic, but really we are here for some science. And so the beginning, according to general relativity, was somewhat different. So the beginning, according to general relativity, was mapped out by Friedman and Lemaitre in the 1920s, both working independently. So they discovered that if you've got some matter in space, space expands, distant objects recede, and they recede, as we know, with recession velocity proportional to distance. And if you have a gas in there, the gas cools. Also, the wavelength of light is stretched, and indeed the universe has a beginning in time. And this was dismissively called the Big Bang by one of the Big Bang's opponents, Fred Hoyle, but the name stuck. So the reception for these ideas was actually not too positive. Einstein didn't like it. Your calculations are correct, he wrote to Lemaitre, but your physics is atrocious. So Lemaitre was obviously a bit upset about that at the time, but Einstein later changed his mind and was actually very supportive of Lemaitre and accepted the ideas wholeheartedly. So of course we now know the Big Bang model is also part of our, more or less, our subconscious in science. The Big Bang made a great step forward in 1948 when it was predicted, of course, because going back in time, the density of the gas was larger, the temperature must be hotter, and the early universe was hot, very hot. And the evidence was predicted by Gamow and Alpha in 1948. And the evidence was found in the 90s and measured most recently very precisely by the Planck satellite. We can now measure the intensity of the heat radiation, the cosmic microwave background, very, very accurately, and that's a diagnostic of the state of the universe at about 400,000 years. We also can, working back in time to higher temperatures, we can make predictions about nuclear reactions that would have happened and predict the proportion of helium, deuterium, and lithium. And just as a function of the one unknown, an unknown or difficult to measure quantity, which is the baryon to entropy ratio, the density of baryons relative to the density of photons in the universe. And it all lines up, the agreed abundances all line up very nicely if the baryon to photon ratio is a little bit above 10 to the minus 11. So we think that this is very good evidence that the Big Bang is correct, and at least we certainly understand it very well after at least back to a minute or so after the initial time. So that encourages us to try and push it back further. It's really a very fundamental question: how did the universe begin? In order to sort of go a bit further, I just want to bring in the idea of, well, bring in the standard model, because this is what we would be testing by looking at the earlier times in the universe. And in particular, I want to focus on elementary particle masses. Of course, nearly all elementary particles in the standard model, whose particles are pictured in this nice wheel here. They all have masses except for the photon and the gluon. These are force-carrying particles of the strong and electromagnetic force. Sort of a question for a long time in physics was where does this mass come from? Where do they get their mass from? And the answer is a very simple answer, and that's that comes from a field, a Higgs field it's called, or it's essentially a mass field. Every elementary particle has a mass which is proportional to the Higgs field, actually apart from the Higgs field itself. So I see that you're standing there. There's a couple of seats here if you want to come in near in the front if you're not too shy. So the masses are proportional to the field strength, and by knowing masses of elementary particles, you can say that the field has a value, and the value is 174 GeV over c squared. As you know, in quantum field theory, if you have a field, you have a particle. So this mass generation mechanism predicted a particle, and these predictions go back to 1964, but it wasn't until 10 years ago, 2012, that it was discovered with a mass of about 125 GeV. Notice I was careful to say elementary particles. If you think of the proton, which actually is most of the mass of our cells, its mass actually doesn't come from the elementary particles, the quarks and the electrons that are inside the atoms. It comes from the energy of the gluon field that sticks the quarks together inside the nucleons. So energy and mass are related. It's the energy of the gluon field that's binding the quarks together that's making most of the mass of an atom. And that confinement of the elementary particles, the elementary quarks inside nucleons, hadrons in general, we'll come back to in a moment. So we're encouraged by our understanding of the standard model established in many experiments and by many people to look further back into the Big Bang to see what might have happened and whether we can trace any relics that might have been left behind. So at about 1 millisecond after the Big Bang, the thermal energy of particles was about 100 MeV, 100 million electron volts, and the universe then was hot and dense enough to melt the nucleons, the protons and neutrons, and release the quarks and gluons that were inside. So before that time, the universe was filled with a plasma of not only electrons and photons, but also quarks and gluons, the particles that the standard model thinks is elementary. So at 1 millisecond after the Big Bang, the universe was quite small. Light had only traveled about 300 kilometers, and that distance, if you scale it up through universal expansion, the expansion of the universe since then, you get a distance of about 1 light year. That's we'll come back to that figure later on. Incidentally, there might still be free quarks and gluons in the universe in the center of neutron star cores. That's a very active topic of research. And this is not some kind of sort of chocolate sweet. It's a kind of a figure that's supposed to demonstrate what a neutron star with a quark gluon core might look like. Okay, so this transition between the phase of quarks and gluons and the phase of hadrons, so neutrons, protons, and pions. Well, the question is, was that a phase transition? And I'll come back to being more precise about that in a moment. So similarly, we can look still deeper into the Big Bang, closer to the beginning, and the Big Bang model predicts that around a picosecond, the thermal energy of particles would have been around 1 tera-electron volt. So getting on for LHC energies, which are about 10 times bigger. And at this temperature, one can predict that the universe exceeded what you could call a kind of Higgs temperature. So it's a little bit like the Curie temperature of a ferromagnet. When you heat a ferromagnet above its Curie temperature, the spins become disordered and the net magnetization disappears. So there's no net magnetization. So thinking of the Higgs field as kind of like a magnetization at very high temperatures exceeding, actually it's more like 100 GeV, but certainly at a TeV, the Higgs field, the prediction is that the Higgs field would have been off. So on average 0. And as I said, the elementary particles' masses are proportional to the Higgs field, so they would have also become massless. And that in particular means that the W and the Z particles, which are the carriers of the weak force, would have been massless and therefore on the same footing as the photon. So that means that one thinks about instead of the weak and electromagnetic forces separately, there's just one electroweak force. So sometimes one calls this the electroweak transition, the transition between photon-like W's and Z's and the massive ones with a short range at low temperatures. So was this change in the state of matter, was that a phase transition? So the conditions of the universe, then we're looking much earlier now in the position of the universe, in the timeline of the universe. At this time, light had traveled only 1/3 of a millimeter, roughly, and that scales up with all the extra expansion to about 3 billion kilometers now. Okay, so let's talk some more about. So we've identified that the state of matter, hot matter in the Standard Model, changes at these interesting temperatures, and I mentioned the word or phrase phase transitions. So what do I mean by a phase transition? Well, I can sort of explain myself just by reference to the familiar substance, which is water. Water has phase transitions, as you know, and let's focus on the liquid vapor phase transition, so which you experience every time you boil an egg. So this at ordinary atmospheric pressure is what's called a first order phase transition. It's got a latent heat. There are phase boundaries, so there's a boundary between the liquid phase and the vapor phase. You sort of see it as a meniscus in a capillary tube, and there's also metastability. So, for example, if you have very pure water and a very clean vessel, you can heat that vessel up to well above 100 degrees centigrade, and you can then release the latent heat by sort of dropping some nucleation sites, maybe some salt or sand in it, and then suddenly it will boil explosively. Things change when you increase the pressure, and so this here is the phase diagram of water. So if you increase the pressure from 1 atmosphere to above 218 atmospheres, or 220 bars, then you find that actually there's no distinction between the vapor and the liquid phase. The first order phase transition disappears, and as you can just move smoothly from what you could call a dense vapor to a non-dense liquid. Everything is smooth. There's no phase boundary. There's no latent heat. There's no metastability. Everything stays close to equilibrium. And down here we have a actual picture of water being at high temperature, close to boiling point at atmospheric pressure. You increase the pressure, and here's the meniscus, the phase boundary between the liquid and the vapor phase. You increase the pressure, and then eventually that disappears. You've just got one sort of semi-dense bunch of water molecules. Incidentally, in between, this line of first order transitions ends at a point, the critical point, and at the critical point you actually have a second order transition as you move from one side, as you decrease the temperature. Now, I'm not going to say anything about second order transitions. They're quite special, and they're not going to be they're quite special. They don't tend to occur in the kind of theories that we've just been considering, but we can talk about them afterwards if you like. Okay, so this is the very general look of what phase transitions. There's first order, there's crossover, and maybe second order as well, which is a continuous phase transition. So let's start with the transition at which quarks and gluons become confined into hadrons, at least thinking about reducing the temperature now. So we know that the theory of quarks and hadrons is quantum chromodynamics, QCD, and there's actually lots to QCD. QCD is a very complicated theory. It's a strongly interacting theory. That's what's doing the job of confining the quarks inside hadrons. And you can look at not temperature and pressure, but temperature and equivalently chemical potential for the quarks and hadrons. So for the early universe, the relevant thing to think about is the fact that, as I was saying, the Big Bang nucleosynthesis tells you that the baryon to photon ratio is very low, so that means that the chemical potential is very low. So the early universe cools along this axis, and lattice QCD can tell you how the free energy of the system evolves, and it evolves very smoothly. So free energy or pressure. So if this was a first order transition, you would expect to see a kink as the system moved from one phase to another, but this is very smooth. So the transition from the quark gluon plasma to the hadronic phase is a smooth crossover, like a supercritical fluid. So you expect very small departures from equilibrium as you reduce the temperature by expanding the universe. Incidentally, up here at high baryon chemical potential, this is sort of the realm that you expect to look at in the centers of neutron stars. Compared to MEVs, although the neutron stars are kind of hot by the everyday standards, compared to MEV, they're still rather cold. So neutron stars kind of live on this axis, the x-axis. Okay, so QCD is a crossover. So what about the standard model? So we're talking about the electroweak transition, the transition from the separate, from the unified force to the separated forces, and the transition from massless to massive elementary particles. So there, now we're talking about, again, we're talking about very low chemical potentials. We can essentially set it to 0. And what that means is that pressure is a function of temperature only. So we can't plot a temperature pressure diagram, but it's interesting and instructive to instead plot temperature against an important parameter of the standard model, which is the Higgs mass. And don't forget, we didn't know what the Higgs mass was until 10 years ago. So this is the way people were thinking when they were doing the following calculations. And the calculation is basically what is the free energy of the standard model at around 100 GeV, because that's what you need to calculate the phase structure. So so it's understood, of course, that there are two phases: the phase with the Higgs field on, which is called the Higgs phase, and the one with the Higgs field off, where there's the symmetry between the W and the Z and the photon, which we'll call the symmetric phase. This work in the 90s by some Finnish colleagues established the phase diagram in these parameters, so that there's a line, just like in water, there's a line of first order transitions ending in a second order transition. And if the Higgs mass is too high, you have a crossover. And if the Higgs mass is too low, or if the Higgs mass is low, you have a first order phase transition. So you can think of the transition as, if you go as a condensation of vapor to liquid. So turned out that the Higgs mass was 125 GeV. And so then the work of the 90s tells us that the Higgs is like the Higgs, or the electroweak transition, is like a supercritical transition. So both QCD and electroweak transitions are crossovers. And some people get very anxious if you call them a phase transition. They say, no, it's not a phase transition, it's a crossover. But I'm not quite so pedantic. Sometimes I will say phase transition to include crossover. Okay, so that could be the end of the colloquium, but let's carry on, because most particle physicists, I think most people think there is more to discover in terms of particles and forces. Actually, maybe we could do a little poll. Who thinks there are more particles and forces to be discovered? Who thinks there are no more particles and forces to be discovered? And okay, so there is a sizable majority in favor of more particles and forces, but there are also some people who are not willing to commit either way. Yeah. So the argument that there are more particles and forces is that the standard model is not complete, and we know that it doesn't have obvious explanations for the dark matter in the universe, the slight preponderance of matter over antimatter in the early universe, and of course, it by design it never set out to do it, but it doesn't include gravity in a quantum field theoretic description. That's what the standard model is. And the standard model is also rather strange as well. It begs, it wants you to ask lots of questions. Why this replication of structure? Why 3 families of fermions? Why are neutrinos so light compared to the rest of the particles? Why is the Higgs mass what it is, 125 GeV? Why isn't it bigger or smaller? And there are more, but this is 3 of the questions that came to my mind. Well, probably at the uppermost of my mind. And so this encourages people to go beyond the standard model using the things that we know about elementary particle physics. Basically basically we know that there are Higgs fields, so why can't there be more Higgs fields? Why only one? These could help building extra models, which would have some dark matter particle in it. Also some symmetry violation, which would help with the matter-antimatter asymmetry. So that would be just fiddling around with the, that would change the electroweak transition in a sort of, in a way you could, I'll come back to that, how it would change may change the electroweak transition. It may be that the electroweak transition is actually part of some bigger structure which has some QCD-like interactions in it, which are doing their own confinement at a higher scale. So that comes under the generic name, well, many names over the decades, but at the moment it's called composite Higgs. So the idea is basically that the Higgs is not an elementary particle, it's more like a pion, and there are some more particles inside it waiting to be discovered. Yeah, generally speaking, there are more ways, introduce more fields, you get more forces, more particles. One way which used to be very popular, but as people talk about it less now, is supersymmetry, which is very nice because it relates the force carrying particles, the bosons, to the matter particles, the fermions. It's a symmetry which we clearly don't see in today's universe at our energies, but it may manifest itself at much higher energies. There may be more dimensions than the ordinary 3+1 that we tend to work in, and particles may not be the elementary objects at all. It may be that they're actually made of string, quantum string. So there are lots of ideas beyond the standard model, and particularly there needs, say, the majority of you are with me in saying there needs to be something. We need to think about things beyond the standard model because of these problems with the standard, because of the problems. So, so what does that mean for phase transitions? Well, it's kind of a good thing because if you introduce new fields, new degrees of freedom, new interactions, it turns out that you're quite likely to introduce, at least in a large parameter space, a first order transition. So for example, if you add more Higgs field, you get more bosons, and more bosons, well, you can, without actually going into the calculation of how it's done, more bosons make the transition more likely to be first order. So I don't know, you can sort of effectively think about it as being like it reduces the effective Higgs mass at high temperature. So it makes it into a first order transition. And with the composite Higgs, where you have the Higgs is like a pion, there's got to be some strong interactions which bind whatever new elementary particles there are. And these new QCD-like interactions, strong interactions, may their quark-hadron transition may be first order. And there are many such theories that are known. We don't know which, but we don't know which of the theories would be the right one for this composite Higgs model, at least not without further experimental probing. So beyond the standard model, there may be first order phase transitions. And a first order phase transition would therefore, because the standard model doesn't have one, would be a sign of new physics, complementary to actually looking for the particles themselves that are involved. Okay, so how do we look for a first order transition in the early universe? So in order to answer that question, so let's just make a little advert on how the phase transition would proceed. And it's a little bit like taking the cap off a fizzy drink bottle. So you know that the carbon dioxide is in solution, and as you reduce the pressure, then suddenly the equilibrium phase is actually separated. The carbon dioxide comes out of solution and makes a gas. So it's kind of a fizz. The And what you saw there was the bubbles, numerical simulation of bubbles of the new phase nucleating and expanding and taking over the universe. So this kind of process releases energy, latent heat, and that heat actually stirs up the fluid. Well, I'll come back to another numerical simulation to show it, but here are a few stills. So this is the kinetic energy in the fluid, and stirs up the fluid and makes shock waves and, well, in fact, pressure waves. And these pressure waves, which are sound waves, these sound waves, when they collide, inevitably make gravitational waves, and we can come back to that. So the question is not whether the gravitational waves are there. They are, but are they loud enough to be detected? And if so, how can we, how can we extract information about the thermodynamic parameters of the phase transition itself? So what about gravitational waves? Well, we know that we are now in the epoch where gravitational waves are very definitely a thing. Ever since 2015, where we detected using laser interferometers gravitational waves of frequency about 100 hertz. And they're all coming from merging binary compact objects, mostly binary black holes. So far, we've got one binary neutron star and one candidate mixed. It's not quite clear whether it really is a black hole neutron star pair. Observations are continuing. It's rather exciting. It started in May this year, and so far you can, as of 2 days ago, there are 39 new candidates, and you can go and check this website to see what it is today. And also, excitingly, this year, a different kind of detector, pulsar timing array, which basically looks for, so I'm sure you know, a pulsar is a very regular clock, or a set of very regular clocks spaced out around us in the galaxy. And if a gravitational wave goes by between us and the pulsar, the arrival time of the pulses changes in some predictable way. And so the North American Nanohertz Observatory, Gravitational Wave Observatory, NanoGrav, has been measuring such pulsars, dozens of such pulsars over many years, at least a decade, and measured a variation in the collective arrival times of all the pulsars, which are consistent with a stochastic background of gravitational waves of frequencies around a nanohertz, or a few nanohertz. And the other pulsar timing experiments, European and Australian, also support, but their data is not quite as good, this detection. And the leading candidate for such a background, which has this kind of a power spectrum, are merging supermassive black holes. We certainly know that supermassive black holes exist, and when galaxies merge, they're quite likely to end up with a binary supermassive black hole. But one can also use it to test for unexpected things, like phase transitions and also cosmic strings. So this is frequencies of around 100 hertz, nanohertz. Well, let's think about what frequencies those correspond to in the early universe. So let's go back to the QCD transition. Remember, that happened at about a millisecond. And so nothing could be generated with a frequency less, or a period less than a millisecond at that time, which would mean that the lowest possible frequency would be around 10 nanohertz. So that is significant for the pulsar timing arrays. So that's an interesting frequency, but of course it wouldn't be the QCD transition, because we know that that's a crossover, but it might be something happening in an as yet undiscovered set of particles and fields at around that temperature. Electroweak, the minimum possible frequency is about 10 microhertz, and then above. So that's LISA, which I'll come back to. And LIGO at 100 hertz, well, that corresponds to temperatures of around 10 to the 9 GeV, about which we don't know very much at all. And the sort of the more or less highest frequency that one could imagine being produced is maybe around a gigahertz. And we certainly don't know what happened at the beginning of the universe around about that time, apart from we got some clues from the cosmic microwave background and inflation. And we certainly don't know how to detect gigahertz gravitational waves with sufficient sensitivity. So that I think is a project for the next century. So just to summarize what I said, here's sign of inflation. That's another colloquium. Pulsar timing arrays, terrestrial interferometers like LIGO, and space-based interferometers for the electroweak scale transition. So now it's time to say more about this space-based interferometer that's coming up, LISA. I mentioned it before, laser interferometer space antenna. It's a different kind of interferometry, but it's still interferometry. It's 3 spacecraft orbiting the sun in the same, more or less the same orbit of the Earth, in a triangular constellation, sending laser beams at each other and accurately measuring their relative speed. And that can be used to search for gravitational waves. And the strain, typical strain, the characteristic strain sensitivity is highest somewhere between somewhere around the range of millihertz to a few tens of millihertz. And of course, LISA wasn't built to look for phase transitions. It was basically built to look for merging supermassive black holes, a little bit lighter than the ones that could be producing the pulsar timing array. So maybe 10 to the 5 to 10 to the 7 solar masses. But LISA can also look for something that is produced in the early universe, as I was arguing, at around the 100 or GeV or above. And here's a sort of a cartoon of what such a signal might look like. And we'll come back to what gravitational wave signals look like in phase transitions later on. Well, actually, that brings me to the next topic, which is how indeed do you calculate the gravitational wave signal from a phase transition? And it's a bit of a challenge. Because ultimately you're trying to connect your particle physics model, which particle physicists like to formulate in terms of a Lagrangian, and you're trying to connect that to a possible gravitational wave detector signal, and thereby understand the sort of connect physics beyond the standard model to the very early universe. And so there's several difficult stages to this program. First of all, you need to understand the sort of the thermal physics at extremely high temperatures, and so that you can parameterize the important parts of the important features of the phase transition, which I'll come back to. So once you've done that, you need to zoom out a bit and study the hydrodynamics of the fluid made of this plasma of particles from your beyond the standard model Lagrangian, and that's that's certainly a relativistic problem, and it may be a general relativistic problem as well, over and above just the fact that you're thinking about gravitational waves. Then you need to understand. Once you've computed the gravitational wave power spectrum, you need to understand how those gravitational waves show up in your detector. In particular, the astrophysical foregrounds, how they interfere, and also, of course, your detector noise. And the general idea is that you want to be able to at least go through this this chain from phase transition parameters through the hydrodynamics to the signal, and then do some parameter inference, first of all, to look at the phase transition parameters, and then ultimately to the particle physics Lagrangian, which incidentally, you may have some other constraints from, at least by the time LISA goes up, from terrestrial experiments, colliders, LHC. So then I just need to give you a very quick survey of what I mean by the phase transition parameters. What are the sort of key features? Well, first of all, there's the temperature at which this fizz goes off. So then you call that the bubble nucleation temperature, or the nucleation temperature. The speed with which the transition completes. How quickly does it switch over from the metastable phase? This is the fraction in the metastable phase to the stable phase, and that is actually also characterized by a rate. So the inverse rate is this time, the time that it takes to switch over. There's the speed with which the bubbles of the new phase expand. There's the amount of energy that they release as a fraction of the total energy, or it's conventional to do that as a function of the total heat energy. The sound speeds in the two different phases. And so these are the sort of the thermodynamic parameters. From those, you can derive some more hydrodynamic parameters. The mean spacing of the bubbles divided by, and it's convenient to think about that as a fraction of the Hubble length. The kinetic energy fraction, how much of the latent heat is converted to kinetic energy, and that's combustion theory comes in there. And the ultimate thing you want is the fractional energy density in gravitational waves. And incidentally, there are two timescales that come in here, one of which is the duration of the sound waves that are causing the stress that's sourcing the gravitational waves, and the other is the coherence time of those stress fluctuations. The more coherent they are, the louder the louder the gravitational waves, the bigger the amplitude. Okay, so those are the things we'd like to calculate, so I'm going to just go through very briefly now, coming towards the end, just some three areas which I have been working on recently, which I think are interesting and challenging. And the first area is inspired by the work here. I'm sure you know from David and Jorge and others in the group that a very interesting way of studying strongly interacting quantum field theories like QCD is through this through holography. So it's through a connection between quantum field theory and gravity, which is first established quantitatively in string theory. And so the idea is that you can study quantum field theory at high temperature, including its dynamics, which is not really accessible any other way, by studying classical gravity with a horizon, and also a negative cosmological constant in a higher dimensional space. So Jago and David put forward a few years ago, perhaps one of the simplest possible model of a field theory with a phase transition. We know what the gravity is. The difficulty with holography is that you don't really know what the field theory is, but nonetheless, this does define a quantum field theory with a strongly interacting quantum field theory with a phase transition. And so one of the things, I find that very inspiring, so we went and calculated some interesting parameters for the phase transition. And generically, we found that actually there's a lot of latent heat released relative to the total heat energy. And also there's some interesting variation in the sound speeds below its ultra relativistic value. So that's sort of one aspect of the sort of the fundamental physics, the extreme thermal physics of calculating some of these thermodynamic parameters. Of course, once you've got to the understanding what the equation of state of the theory is, then you would like to simulate a fluid of that substance. And here's simulation in some effective theory where you've replaced all the unknown stuff just by hydrodynamics plus one scalar order parameter, which you can think of as the Higgs. So there was a phase transition going on, and what you're looking at here is the speed of the fluid. So you can see that there are lots of interesting structures in here, in particular shock waves that continue to sort of echo around the universe long after the transition has completed. And we calculated the gravitational wave power spectrum, and it's sort of that's the blue line, or rather, this is actually the growth rate, because the gravitational waves continue to grow just as the sound continues to echo around. And these more smoother lines are the result of theoretical prediction from what we call the sound shell model. The idea is that this sound, these sort of pulses of sound echoing around the universe are generating the gravitational waves. So I think I'm getting a little bit short of time, so I won't go into explaining anything about the model, but it does make predictions, and here are some predictions of the gravitational wave power spectrum as a function of one of the parameters of the transition, which is the wall speed. So you can see there's quite a change in shape of the wall speed as a function of wall speed, and that's actually very interesting and relevant. So with this model, one can go and calculate some, or make some estimates of signal to noise ratios at LISA as a function of these various thermodynamic parameters. So here we've got some reasonably big bubbles, a tenth the size of the horizon. Here is and then the signal to noise ratio is plotted on the left, a tenth the size of the horizon, on the right, 100th. And I think I'm running out of battery, so it's probably a good thing. I have to stop. As a function of the strength of the transition, the amount of latent heat released on the y-axis, and as a function of the wall speed on the x-axis. And so for reasonably strong transitions, one can get very large signal-to-noise ratios for transitions at around 100 GeV. And this is the worst case scenario where you can't remove the foreground that's going to be there from binary white dwarfs in our own galaxy. But if you can remove it, because there's actually an annual variation in that signal, because as the detector orbits the Earth, then you can do a bit better. So that emphasizes the importance of understanding how to do parameter fitting for the actual gravitational waves signal. So finally, I just thought I'd mention that there's a potential skeleton in the cupboard, because I confidently said, oh, the Higgs fizz goes off, and we can calculate the speed with which it happens, and that's all based on something called in condensed matter theory called homogeneous nucleation. And there is actually he's never actually been experimentally verified, this homogeneous nucleation theory. And there's this long-standing puzzle about the first order phase transition between two phases of superfluid helium-3. So the idea is that the rate, because it's a sort of a thermal fluctuation that gets you over a barrier, the rate ought to go like the exponential of some energy, the barrier height, which is in fact the energy of a small bubble of the new phase divided by the temperature. And the theory of helium-3, which is, by the way, very, very well understood, predicts that this ratio should be 10 to the 6. So e to the 10 to the 6 is, in terms of a lifetime, is a very big number, and it actually doesn't matter what units you use, you still get a big number. You could use seconds or ages of the universe, it's still a big number. But actually in the lab, metastable helium-3A only lasts for a few hours or days at most. So I'm involved in a collaboration with condensed matter experimentalists to try and understand what's going on and also to study the propagation of the phase boundary, to learn something about how to calculate wall speeds. So here's some experimental results that are sort of preliminary. It's we've been you cool the experimental cell, and you wait for the through the A-B transition, and you wait for the A phase to appear. And this is the time plotted there, and it's a very nice exponential. So it's certainly obeying something like this energy barrier formula, but just with completely the wrong exponent. All right, so what are the future challenges? Studying the hydrodynamics of strong transitions, which the holography and other theories tell you could be the case. So in particular, the appearance and of shocks and turbulence. What about the self-gravitation of the fluid itself, which becomes important when the bubbles grow to being an appreciable fraction of the Hubble length? Also, the secondary gravitational wave production by the curvature perturbations that are induced by that process. As I was saying, the efficient and accurate calculations of the thermodynamic parameters from underlying models, because we don't know what the model is yet, and how to distinguish phase transitions from astrophysical foregrounds. And something that I haven't mentioned at all is how to connect that to future collider data. So to summarize, we've been addressing the question of what the universe was like at age of about 10 picoseconds. What particles and forces were there, and maybe we can answer or constrain whatever new physics is there to be found. If there's a first order phase transition, the Higgs field or something like it will turn on, make a fizz, gravitational waves, and those gravitational waves have a lot of information in them which can be extracted if we're lucky enough that they're loud enough to be detected. And we're going to be looking for those gravitational waves in the next decade at LISA, Laser Interferometer Space Antenna. And it's at least we'll have some information about the state of the universe at 10 picoseconds from it. And this will be complementary information to whatever new physics we find at LHC and other experiments. So thank you very much.
Yeah, thank you, Mark. Thank you, Dr. Knight. Colloquial, and now it's time for questions.
Yeah.
All right. So better. Yeah. So I was thinking something. So can you make actually the Higgs lighter, so to have a phase transition, but with gravity interaction instead of introducing new particles?
Sorry, can you say that again?
So suppose the Higgs is not minimally coupled to gravity, so it has another interaction.
Mm-hmm.
Then is that possible to make it actually effectively lighter during the crossover, so that it is a first order phase transition? Is there a way to, or do you need, I mean, the only way is to introduce new particles?
That's a very good question. I never thought about it before. I suspect that non-minimal coupling would be quite difficult to implement at the level that wouldn't mess anything else up, because it's, you're thinking
Possibly.
about yes, so you're thinking about curvature times Higgs squared terms in the.
No, that would make I think heavier. So maybe derivative coupling, so other things.
Yeah, it's an interesting. Yeah, that's an interesting question. But the thing is that the curvature is like Hubble squared, and so that whether all this you of course choose the sign of the coupling constant as to whether it makes it
because you have to suppress by a scale that is, I mean,
Yeah,
lower than that. And
yeah, so you
but,
would,
but in any case, you are a high energy, so it's
Yeah.
not going to screw up anything of what we know on Earth experiment, I think.
but yeah, so Hubble squared is competing with, on the other side, Higgs mass squared. So there's a big separation of scale. So you, in order to have to make it work, they need a very big parameter. So so I think the answer is not in the usual cosmology, but maybe there's some different, you could get the universe, because we don't actually know that the universe was expanding in its standard radiation dominated phase at that time. So it may be that you could think about a different kind of expansion, which
So you mean that the ratio scale is too large? I mean, the separation scale is too large, and then you would need a new scale that somehow will influence also Earth experiment now.
I think so. Yes. I mean, I'm not saying that
Could
this
be.
is not it can't be done, but yeah, there's one or two things to think about in order
Thank
to.
you.
Would the transition be first order in the supersymmetric version of the standard model?
That's a very nice question. Thank you. The answer is yes and no. I mean, because the supersymmetric extensions of the standard model, have many parameters, and so there are, and of course there are many different supersymmetric extensions of the standard model. So in some of them, yes, and in others, no. But one way that people looked, people that got people excited before the experiments sort of ruled it out was the so-called light stop scenario, and that had a first order phase transition. Yeah, because the stop was a bosonic particle that was helping the phase transition to become first order. But unfortunately, we've got no stops. So yeah.
I have two quick questions. One is about to what extent is it completely established that the electroweak crossover is actually not a phase transition in the standard model? I'm asking because since it's a chiral theory and these are lattice simulations, I imagine this is difficult to do.
Yeah, that's a good question, and that's really about how this calculation that I just sort of symbolized with a Finnish flag, and actually that's a bit unfair because Shaposhnikov is not Finnish, but it's just a majority. How that calculation is done, and yeah, so it's actually more complicated than a lattice calculation, and actually the lattice calculation is the thing that I would be most confident about, because it's really just three-dimensional statistical mechanics, and that's you can really, because it's only three-dimensional, you can get good statistics. But it's the connection between the four-dimensional theory and the three-dimensional theory that I'm not so, in my own mind, certain about, because that's a perturbative calculation, very impressive perturbative calculation. Use an expansion in powers of the weak coupling, but the weak coupling is small, but it's not that small. So the question is how under control that connection between the 4D and the 3D theory is, and I'm not certain about that in my own mind. It doesn't. So you have to get somebody to come and give a talk and try and get them to convince you.
Okay. The second question is about this secondary signal that you mentioned.
Yes.
In black hole mergers, people talk about a secondary signal.
They do, yes.
And they mean this memory effect generated by the own back reaction of the gravitational waves.
Okay, yes. That's not what I meant by
That's
secondary.
okay.
So by secondary, I meant, I mean, indeed, when you have primordial black holes, they're made out of some density, initial density perturbation, which also has a associated curvature perturbation. But in general relativity, those curvature perturbations themselves can generate gravitational waves at higher order. So it's a higher order effect beyond linearized GR.
I think that's what people call the memory effect.
Do they?
No, maybe not. Maybe wrong.
Anyway, okay.
Questions?
Thanks for the talk. I was wondering about the white dwarf mergers that you mentioned. They're essentially noise for you, right? So how noisy are they compared to the signal that you expect?
Yeah, here's a sketch. Yeah, very good question. They said they're not merging white dwarfs; they're just orbiting. Yeah, so it's really pretty much Keplerian orbits. So they're sort of a very pure, more or less single monochromatic signal. But the galaxy is supposed to contain about, nobody actually knows, 20 to 30 million of them, of varying masses and compositions. And so modeling of this foreground is, a whole subject in itself, but this is a cartoon of what it might look like. LISA is supposed to be able to detect the loudest ones. Maybe the previous and earlier slide will be a bit more informative. Here we go. Yeah, so there will be about a few tens of thousands that are loud enough in the right frequency to be detected, and this is what this kind of all these dots are supposed to mean. And there are some that we already know about that will definitely be a signal, and these are these stars. They're called verification binaries. They'll be a superb way of calibrating the instrument. But once you've detected those, there'll be a whole bunch of all the other tens of millions that are not detected and make a confusion noise. And here's another sketch of it. So the answer is, it's sort of a little bit hidden. A preliminary answer is to your question is hidden in the difference between these two graphs. And to a certain extent, it depends on where the phase transition signal peaks. I mean, one of the things we're pretty sure about is that the phase transition is a very peaked signal, and the peak is controlled, as I mentioned, by the average distance between the bubbles once the transition's gone off. So if that distance is not sort of a the optimal thing is for the frequency to be the peak frequency to be a few millihertz, but there is sensitivity either side, providing the signal is loud enough. But yeah, the white dwarfs are a problem, but they're not a fatal problem. They just compromise the sensitivity in a certain frequency range.
I'll take just one more question from the crowd.
Thank you. Is there some intuitive reason as to why the Higgs field turns off at these high temperatures that you said?
Yeah, I think I tried to give some intuition with the comparison to a ferromagnet, and it's another way of thinking about it is that the equilibrium state is the minimum of the free energy, and the free energy has two components, one of which is the field energy of the Higgs itself. Like the electromagnetic field has an energy, the Higgs field has an energy density, and then there's also the free energy that's in the plasma, all the particles, all the hot particles, and that depends on the masses of the particles, and the masses of the particles depends on the value of the Higgs field. And it just happens that if you increase the temperature, then the minimum of the free energy, it becomes energetically favorable for the Higgs field to turn off.
Okay, thank you.
Okay, so I think it's a good time to stop. We had already a nice discussion. So thanks, Mark, again.
Thank you. Yeah.
Before we go off, I just want to remind you that Mark will be here tomorrow in case you still want to talk to him. And the students are also welcome to meet Mark today at 4. He will be available in the seminar room for discussion. That's it.